Welcome to another computer episode by Fulzor. In this episode, we will be discussing how to make a stack CPU from bare minimum components. Very similar to the accumulator video, but this will use a completely new architecture. So I hope you enjoy. Okay, so welcome back to the simulation. And in this episode, we are going to build a stack computer. So the other episode of how to build a computer tutorial did really well, and that design was a accumulator CPU design. So if you remember, we had this central register called the accumulator where all the arithmetic went into after. But in this episode, we are going to build a stack computer or stack architecture. So first of all, let's explain what stack architecture really is. So let's imagine that we have a stack of plates, just paper plates on a kitchen counter, and each plate has a number on it. So if we want to access a plate, we have to grab the top plate, only the top plate, because if we grab a middle plate, we just can't, because then all other plates are going to, drop down. But we can remove the top plate and put it on the bottom, or we can remove the bottom plate and put it on top. And that's effectively what a stack register is. All of the numbers that we want to access are in stacks, but we can only access the top stack. And we can only move numbers either to the bottom of the stack or from the bottom back up to the top of the stack. We cannot directly access the number in the middle of the stack. And our opcodes, of course, are going to be a 4-bit number, so 0 through 15. And really, there's not that many opcodes. So our stack computer is only going to add. So we don't need an add opcode. But again, if you want to be able to do different arithmetic, you would need opcode for each arithmetic situation you want to do. But in order to access the registers, all you need is a push and pop command, which is what they're called. So push means that we're putting data onto the stack. Yes, we're putting data onto the stack, and pop means we're putting data off of the stack onto the bottom. So push means we're putting data onto the top of the stack, and then pop means we're removing data and putting it on the bottom of the stack. So this allows arithmetic to be easily computed. So since we're only fooling with the top of the stack at all times, it's kind of like doing an equation of like order of operations, because you can only do one thing at a time and then you move on to the next situation. For example, let's say we have parentheses 4 plus 2 times 3. So the first thing we got to do is add 4 plus 2, which is 6, and then we multiply it by 3, which is 18. So it's a very linear progression of what we have to do, which is very stack-like, because we add 4 plus 3, then we remove that, and then we take that sum and we multiply it by 3, which would be the next plate on top. I hope I explained that pretty well. This is pretty fun to make, I'm not going to lie, but it was extremely tedious to do. It wasn't as straightforward, in my opinion, as an accumulator CPU, because you got to figure out a way to make the push and pop mechanic work well, which seems pretty straightforward. You just like progressing forward or going backwards, but it really isn't. So just like the other video, we're going to make a completely new simulation, and we're going to do it, but this is what the final product should relatively look like. We'll have an ALU, we'll have the secret stack register, then we'll have the output register just so we can output what our final data is, and then we'll have our opcodes, and we'll have a little manual program counter this time, just to save space. So let's make a project. We're going to call this stack. So again, we are beginning with the NAND gate. I'll have timestamps too if you don't want to listen to this, because I know most of y'all already probably watched the accumulator CPU tutorial, but hey, if you're new to the channel, might as well stick for this. This is pretty cool stuff. So, NAND gate, right? NAND gate is the father, the grandfather of all logic gates actually to ever exist, because you can make a computer with just NAND gates. So this is the atom of computer architecture, the Adam and Eve in that sense, not like a microscopic atom. But NAND gate, if one or the other one is on, the output is on. But if both are on, the output is off. So beautiful, beautiful. Now let's make a NOT gate out of this. So we just kind of combine the two gates, and we get a little inverse. Save. NOT. And then we make a new chip, Oops. And now look at this. Beautiful right here. So if both of them are on, the output is on, and gate. I'm going to kind of speed run this too, because this is basic stuff. I have other videos about this. I'm sure you don't want to hear this. But hey, we're going to start from scratch on every single computer architecture video to make sure that none of y'all get lost. New chip. So now we're going to... So look at this. So this is an OR gate. So if either or one of them are on, the output is off. So this is actually a NOR gate. Oops, whoops, my bad, guys. NOR. Take the NOR. And this simulation is called Sebastian Lague digital logic simulation. I'm sure the comments are going to blow up about what's the name of this simulation. I'll say it right now. I'll put it in the description too, just so I don't have to keep re-answering the same question. It's Sebastian Lague digital logic simulation. It's awesome. Go check out his channel. His channel is awesome. But yeah, I'm very grateful for this little simulation. So we are making these basic logic gates. We're going to make the XOR. That's personally my favorite one. That's what the channel is named after. The XOR gate. And it's just fun to kind of set it up. There we go. So if both of them are on, it's off. And then these are my favorite type of videos to make, because computer architecture really is just, it's such a mystery how the software works with the hardware in such a beautiful way, you know what I mean? So this is XNOR, and this is the last of the basic gates. So now we can go on to, we'll go into memory real quick, just because we had that one D latch to save the output. So this should be pretty easy, just to make this little simple D latch. Actually, we're gonna do this. So the actual physical CPU that I'm making too, progress has been very, very slow. I've been very busy recently, so I haven't had a lot of time to really hone in and dial on it. But it will not be neglected. It's just very hard. So okay, there we go. I was about to freak out. I thought I didn't do right. This is the see, if I get quiet, that's how you know something's not happening the way it should. So this is the data, and then this is the store. So let's toggle this so we can see. Oh, it doesn't work. Fire. So preferences on toggle confirm. Well, that's the wrong one. Preferences, hover, toggle, confirm. There we go. So now we can see it. This is our little delatch. So new chip, 1, 2, 3, 4. And then we can make a little dereg, 1, 2, 3, 4, 5. One, 2, 3, 4. Boom. So yeah, nothing big happening. Nothing, no rocket science. Because this is computer architecture, but oh man, excuse me guys. Okay, there we go. So look, this is the register. Beautiful, beautiful, beautiful. I'm gonna call it D reg. And then we're also gonna make, of course, the ALU. And then after that is where things are gonna start to like differentiate itself between the accumulator CPU. But hey, you don't need to watch the accumulator CPU episode to understand how this works. So this allows us to store data pretty easily, very straightforward. Now we need to learn how to just add. All we want to do is just add data. So how are we going to do that? We are going to do that by making an adder. So there we go. Got a little half adder right here. Just gonna call it half. Just half. New chip. So 2 halves. 2 halves make a whole. 1, 2, 3. Okay, so there we go. We're going to edit this. This is A. This is B. And this is the carry. And then do we have, I'll put carry 2 and some. So in case you think I did some little voodoo magic, it kind of is, not going to lie. But if this is all ones and then we count this as decimal and this is the ones place and this is the twos place, 1 plus 1 is 2, plus 1 is 3. This is 1 plus 1 is 2. And there we go. So we have a full adder. And then we can chain these up to make a 4-bit adder, which is exactly what we want. And look how small these modules are. Oh, I screwed up. There we go. Okay, there we go. So this is it. This is the full adder right here. 2 plus 2 is 4. 2 plus 4 is 6. There we go. Then we have 6 plus 4 is 10. And it works fine. So as you can see, we're kind of just comparing the numbers. Are they the same? Are they different? They are. Then we're going to carry the 1. And that's why they're all connected like this. So also full adder episode if you're interested in this. But this is going to naturally be a long episode. And there's a lot more explaining to do than just this. So, but this is our for adder, for add. Okay, so we're done. Now let's go on to the cool stuff. So we are going to make a JK flip-flop, which is going to be crucial in the stack design, not necessarily the program counter design, in which you'll see, if you don't know what a JK flip-flop is, then that's fine. I'm going to show you. So actually, it's going to be a data flip-flop, so not really a JK flip-flop, but they're almost identical. So almost identical. And it's almost identical to two, actually it is kind of two data latches just chained together, which is interesting. Very interesting, cool little design, but it isn't quite that. And you can see my actual transistor video on how to make a JK flip-flop, which is pretty interesting if you ask me. How this works. How this works. See if I can do this right first try. No, it's definitely second try. Okay. Well, I did type that out, whatever. This is data. Oh yeah, it works. So look at that. This is another way to store data. But first, there's two differences between this and the D latch. So I want you to pay attention. Listen up. Listen up. So if the data is on and the clock is on, we store. Just like that. But oh yeah, I was like, what the heck? I didn't do it right the first time. You were right. So this is why I was a little freaked out. I'm not gonna lie. So it's like, what the hell? But this is it. Yes. So notice if the clock is on, we can change the data, but nothing happens. Nothing happens to the output. It actually only saves the output when the clock goes from high to low, which is really cool and really useful in this architecture for some reason. And as you can see, doesn't matter. It only goes down. So this is called a D flip-flop, a data flip-flop. So the data flip-flops, between data, which is cool, which is really cool. So guess what we're doing with this? We're making a 4 data flip-flop. So we can make a 4 register. Wow. Rocket science, bro. This is rocket science. They say this is hard. It ain't hard. It's pretty hard. It's pretty hard. I mean, I wonder who actually thought of this. Who was like, I'm making a stack CPU today, boys. I'm gonna devote my whole life to making a stack CPU instead of a better one. I like the stack. I don't like the stack. But this is it. Look, the data works. It works. So we're gonna go with a 4 data flip-flop. New. Okay, so now I'm gonna show y'all a phenomenon with this. Actually, do I want to? Yeah, I'll show you now since we're on the topic of data flip-flop. So if we get 4 of these, which our stack is only gonna have 4 slots, so it seems to be a central theme in our computer architecture is 4. So if you chain these up, just like this. Oh man, I misclicked. Now look closely at these data flip-flops, okay? The data is going to move every clock pulse. You see that? If you didn't, I'm going to do it better. So right now we have the 4 going into the first data flip-flop. We save it. We save it. Then we clock, or we pulse the clock again. This is the clock module, okay? And look at that. The 4 is moving along. It is moving along the data flip-flop, which is crazy. Like, how is it doing this? Oh man, we had a little glitch. Sometimes this program glitches. I don't know why it does that, but it does not make me happy. But look at that. So this is how we're going to push data. Remember the 2 opcodes I said were push and pop? Pushing the data forward. Op means we're putting the data backwards. This is how we're pushing data. So we have like half the stack register already done. But this is by far the easy part. So now we're going into the hard part. The hardest part of them all. So new chip. New chip, we're going to make something called a dude, I can't think of the name. A multiplexer. Wow, that was bad, bro. That was bad. I could not think of the name. Who am I? Who am I? Man, I'm going insane from this, bro. This is going insane from designing all these circuits, bro. All these circuits. So 1, 2, 3, 4, 5. Yes. 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 So look at this. Look at this. Man, this is so cluttered. This is so bad. Oh my, fumble. What an absolute fumble. Okay. Beautiful multiplex. I mean, look at this. Beautiful design. All the wires are so organized. They're so organized in the multiplexer. But basically, we can switch. Wow, I really actually just screwed up this multiplexer. This is so embarrassing. This is terrible. Absolutely tragic. Dude, I'm so sorry, guys. I'm just not thinking today. So I'm so sorry. Okay, so multiplexer, we can swap between data sets. Very easy, and very useful. Very, 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 very useful. Oh my gosh, what the typo after? That's because this camera's on my keyboard. So kind of an L step on my part, but you gotta do what you gotta do. Oh my gosh, what? Dude, misclick after misclick. Okay, cool. Save this. Multiplexer. Okay, so now another part we need to make is the increment system, which you'll see how that's important too. So we just need to make a little device that can that will add 1 and increase by 1 every pulse, which is all we need to do. So we only need to go up to 2 because we just need to go up to 4. So it shouldn't be too complicated. So we should be able to get away with this with half adders, right? I'll go full adders just to make sure. But um hmm hmm so I need to look at this real quick. This is a little interesting of a circuit. Totally didn't just edit this out because I had to relook to see what I was doing. Not happened. But yeah, anyway, so let's get on with this incrementer. So every clock pulse is going to increment by 1, which is cool. It's very easy to make too. I mean, super easy to make. I can do this with my eyes closed. I know exactly what I'm doing. Not hard at all. Not hard. I don't know why we had this cut in here, but it wasn't because I didn't know what I was doing and I had to go look at the circuitry. No, 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 no. Mhm. Oh yeah, look at this. Do every clock pulse we increase by 1. You see that? We go all the way up to 3. So 0, 1, 2, 3, boom. Beautiful, beautiful, beautiful incrementer. It's just so beautiful. So now we need to make a little circuit that can decode this, which is easy. Which is easy. Okay, and then look, we got a little decoder. So now we can cycle through inputs, which is good. So incrementer, increment, good. Let me see something. Yeah, so the incrementer. Yeah, I already said it's a new chip. Actually, we can go back into the stack reg. Actually, no, we can't. We cannot. So new chip. Um, gotta go into the library, get a little bit of a tri-state buffer. There we go. So we're gonna use 3 of these. I mean 4, right? And don't know what a tri-state buffer is. Video is video for it. I'll explain it a little bit. We can either enable the output or we can disable the output, which allows us to connect multiple outputs together, which is cool, which is very cool. But I'm going to assume that you know what a tri-state buffer is, just because I know you're smart. I just know that you are smart. Oh man, I'm not smart. There we go. Save. So four try state buffer. Now we go to the stack register, and then we need to add our 4 try state buffers. Yay! 1, 2, 3, and 4. 1, 2, 3, 4. Okay, so we're going to delete this. Man, it's a long long video. Okay. Oh. Gotta get close to these logic gates. So they love you. They love you. These logic gates will love you. Incrementor. My bad. So now we can increment backwards. So watch how we're doing this. Watch closely how we are doing this. High tech. Super high tech. Like, you have to know, be a genius to figure this out. You have to know every move it can make. You have to know where every electron is at all times. All times. So, push, and pop, pop and push to pop. So move forward. Oh, wow. Move backwards. Oh yeah. And we can, so yes, we can, this will move the data forward by physically moving the data forward, and this will move the data backwards by deciding which tri-state buffer gets enabled. So it doesn't physically move the data backwards, it moves the pointer backwards, which is also a stack design little hack. You can call it the SP, which is the, like, I forgot the name of it, but it means it's a pointer that points to the top of the stack, which is what this is doing, in order to get the little push pop effect that we are craving. The push pop effect that we really want. And this is it. So, very cool. Very, very cool. So now we need to add some more tri-state buffers for the bottom section, because in a stack design, there's one stack register that feeds both inputs of the ALU, which is what we need to do now. So both inputs of the ALU will be fed. No one's going hungry tonight. No one's going hungry. No ALU. An ALU without data is a hungry ALU. And you got to treat all your ALUs right. Got to treat them all right. All with love. Oh, with love. Man, this is like right in the middle. It's a little angry, huh? A little angry little ALU. This is fine. We're going to put it right here. Right here. Yeah, so this is about to be an atrocious wire situation. I'm so sorry if you are OCD or like neatness, because this is full Zor, not Mr. Clean. So Oh man, we got, oh, I don't like the way that looks. Mm-hmm. Mm-hmm. Man, 30 minutes. Very cool time. So which one is activated? It looks like this one's activated, right? So if this one is activated, we want the one in front of it to be activated too. So I hope that made sense. So we're going to enable this one. And then if we pop, we want this one to be activated. If we pop again, we want this one to be activated. We pop again, we want this one to be activated. Cool. So now we got that. Now we need a little bit of bus work, a little bus work. Just so we can connect all of these together, right? So 1, 2, 3, 4. 1, 2, 3, 4. Cool. I mean, this is going pretty well, actually. Might be a longer, man, this is going to be a long video. And I do want to put a little disclaimer, like, I'm pretty sure this is how you can make a stack CPU, but I'm no expert. I am in electrical engineering at university, but I'm not in a computer architecture class. This is straight up research about how to make it from scratch, and there's not too many videos about how to make it from scratch. There's some Ben Eater videos about how to make it how to like read the code, but there might be a Ben Eater video about how to make it from scratch. But if there is, I have not watched it. This is my creation, and it might be kind of poopy, but it might be kind of cool. So, but it is kind of cool. You get the fools are cool promise. So there we go. Nice. Oh wow, nice, nice. Man, 38 minutes of my life gone. Okay, 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 okay. Oh man. Wow, I mean, that was some hard wiring work. Let's say this, in case the computer crashes, we don't lose that progress. Now we got these two output systems to feed into both sides of our ALU. So if we edit this, B, 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 cool, very cool. A, 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 A. Okay, we got it. It's all, I know, kind of figured out. The last thing we need to add is the multiplexer, because the output of the ALU will again be fed back into this, and we need to choose whether we want new data or we want the ALU's data. You know, so So we did it. Yay, yay, yay. Congratulations, everybody. We've made the circuit, and now we can push and pop data. What? I know. Very cool. So push, and then we can see its output. So we can pop it and go backwards, or we can push it along. Nice. And then if we push it too far, it evaporates. It goes to nowhere, which is bad, very bad. But now we had the ability to do this, and we don't really use the pop command that much, if I'm all to be honest, but it is here for our convenience. So very, very cool, I'll say. It is very cool. So save, and then new chip, and this is going to be the this is going to be it. This is going to be it. So this is A. A should be first, right? A is a little higher up in the hierarchy. Low key, right? Mm-hmm. So we feed it back. Make this cute little loop shape. Man, this is a long video, bro. We putting some work in today. We put that work in. You know, and then the D-red, whatever, yada yada, yada 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 yada. Oh man. Okay, and I did a lot. We do need to add one more module, which is the opcode module. Not really the smartest person, so kind of forgot about it. But this is the CPU. Yay, hey. This is the CPU. Not gonna lie, this video is kind of long, and I'm kind of tired, so I think I'll do this later. We're back on a new day too. Sorry for the little cut. Now let's make the opcode. The opcode. So, we need a little merge from 8-bit to wait. We need an 8N, right? And then we need a 1, and yes, this is exactly what we need. Okay, so we need from 8 to 1, right? Beautiful, beautiful. And then we need a lot of 3-state buffers. Lots of them. 1, 2, 3, 4, 5, 8. Okay, and then we connect. So this is where we're going to store our code. If you are a new viewer to the computer architecture world, the opcode is... So the hardest part about computers, in my opinion, is how does the software interact with the hardware? And I bet all y'all know, oh, logic gates make computers. It's logic gates. All you got to do is use logic gates. But how do the logic gates work with the software? That's like the real mystery. And this is a key insight on how it works. For like, you know, big programs like Python or whatever, they use compilers, which is very messy. I don't know how that works yet. But an opcode is just a little binary code. So like 6 in this example, and it gets fed to the computer, and the computer can decode that and then produce whatever we want it to produce. So easy way for us to make a little coding segment. So we need 1 to 8 now. And the cool thing about stack computers is there isn't a lot of code. All you have to do is tell the computer what number or what data you want to send, and then you got to tell it either really to push or pop. So pop or push, push or pop. So make sure this is small. Yeah, this is good. Now let's go to the CPU. Take a look at opcode. Only have 4 of these, nothing too crazy right just yet. Need a bus so we can put all the data on this. It's a classic CPU setup by me, just because I think it's the most organized. There we go. Beautiful. So now we can connect this directly up to our stack reg. And we're almost done with the simulation. So okay, so this is it. This is the whole computer. We've officially made a somewhat semi-stack computer CPU. Like I said, I don't know if this is the exact way, but this should be a way. There's a fly in the room. It's kind of bothering me. I'm sorry. But you'll notice a few things. So first thing is, where's the program counter? And if you don't know what a program counter is, got a video for that, so you should go check it out. But essentially, program counter cycles through the opcodes, so we can have different the different codes get fed into the CPU automatically. We're not doing that. We're having this little button manual system right here, just because it's going to make everything a little more fluid, a little more easier, and I don't think it's necessary to understand the architecture. So, and again, you can add more commands to, like the jump command, which is in another video. Man, this fly is so aggravating, bro. But okay, so this is it. Let's yeah, I got it. Let's pop it a few times or push it a few times just to get all the data out of here. And there we go, clear the CPU. And now let's see where the stack, let's see where the pointer is at. So it looks like we are on okay, let's pop it once. We should be good. We gotta pop it. My bad, we gotta pop it again. Okay, cool. So now we are on the first 2 segments of the register, which is exactly what we want. So this is how it works. Let's clear this register 2. Everything is cleared. We're going to do something very simple. We're going to do 4 plus 4 plus 4. So essentially 4 times 3, which is 12. We're going to do that in 4 lines of code on this stack register, which would be, my bad, wait, the numbers on top. So we need to first push 4 into the stack computer. Then we need to push 4 again. And then we need to essentially take the output from our ALU, feed it back into the stack register. So we have to switch the multiplexer, and we have to push so the new data in, and then we have to, and then it adds it automatically for us, and then we can save it onto this thing. So this should work. Okay, so we got 4 in the system. Got 4 also in the system. Then we should save it. And then we have 12. and then we save it to our DReg. So that's it. That's a little simple code. I can't believe that worked this well. Nothing ever works this well in the first try. So, but this is it. This is a stack CPU. This is how it works. We have the push-pull system. We have a multiplexer system to get the output from the ALU back into the reg system. Again, this is a very simplified version, but even the simplified version took almost an hour to explain, and I didn't even explain it that well. But hope you enjoyed. Hope you liked the series. Please subscribe if you're interested. And that's all I got to say. Thank you so much for watching. Have a good day.